The unique k greater than 2 groups of a set are produced by partitioning into subsets the set of elements combining into k equal 2 groups. This mechanism produces set complexity or makes a set into a system. The count of k equal 2 possible groups of the second row of single letters, exactly equals its count of k equal 2 unique groups. There are 10 k equal 2 unique groups, which is the exact possible number of these single letters. These have been partitioned into a group beginning with B, 1, a group beginning with C, 2, a subset beginning with D, 3, and a subset beginning with E, and there are 4. The count of k equal 2 possible groups of the third row of double letters, this group that we just showed was partitioned, doesn't equal its count of k equal 3 unique groups. That's because there are 10 possible unique k equal 3 groups, but there are 45 possible k equal 2 combinations of this set. So, limiting the k equal 2 groupings to elements included in the subsets with the count 1, 2, 3, 4 produces the exact count of k equal 3 groups. For example, there's only one element in the subset beginning with B, so it produces 0 order 3 groupings. There are 2 beginning with C, and CB combined with CA will produce the 1 CBA. In this group of Ds, we can see that the DC combined with the DA will produce the DBA. The DC with the DB will produce the DCB, and the DC with the DA will produce DCA, giving me 3. Now we can look at our groups beginning with E, and we'll see that the EB combined with the EA will give me the one group EBA. The EC will give me 2 groups, EC combined with EA to give me ECA, and the EC combined with EB to give me ECB. And the ED will give me 3, which will be the ED combined with the EA to give me EDA, the ED combined with the EB to give me EDB, and the ED combined with the EC to give me EDC. Now, the count of k equal 2 possible groups of the fourth row of triple letters, that we just generated, doesn't equal the count of k equal 4 unique groups. There are only 4 k equal 4 groups, but there are 45 possible combinations, order 2 combinations of these 10. but again, limiting the k equal to groupings to elements included in the subsets with the counts 1, 3, which equals 1 plus 2, and 6, which equals 1 plus 2 plus 3. This will produce the exact count of k equal 4 groups. For example, for the CBA, we have nothing to combine it with, so it cannot produce k equal 4 order group. But for the 3, we also have a single group, DBA, starting with DB, and since it's only a single group, it can also not produce a k equal 4 order. But for the 2 part of the 3, we have two DCs, which we can combine, DCA with DCB, and we will get DCBA, 1, from that group. Now we have the groups beginning with E. And again, we have the group beginning with EB, which are only one of, so we cannot form an order for a group with just one. But then we have the group beginning with EC, which are two of, and so we can get ECA with ECB, giving us ECBA. Now, we have the group here, 3 beginning with ED. And with this group, we have EDB combined with EDA, which will give us EDBA. And then we have EDC combining with EDA, which will give us EDCA. And finally, we have EDC combining with EDB, which will give us EDCB. So we have the 5 groups of k equal 4, exactly composed from the partitions. Now, the count of k equal 2 possible groups of the 5th row acquired letters doesn't equal its count of k equal 5 unique groups, because for 5 elements, there are 10 possible order 2 combinations, but we only get 1 possible k equal 5 unique group. But again, limiting the k equal 2 groupings to elements included in the subsets with the counts 1, and for the 4, 1 plus 3, and the 3 equals 1 plus 2. So let's look at what's possible. So we have 1, and again, since we only have 1, we cannot combine it with another to produce an order k equal 5 group. And then since the 4 is partitioned into 1 and 3, this 1 also doesn't have another element to combine with to produce an order k equal 5 grouping. Now, the 3 equals 1 plus 2, an ED here, EDB, and an EDC and an EDC. So again, the EDB is by itself, so it cannot combine with another element to produce a k equal 5 order group. And so the only group we can produce is with the 2 EDC groups, and combining those, we get EDCBA, the 1 k equal 5 order group. So, to reiterate, the unique k greater than t groups, these k greater than 2 groups of a set, are produced by partitioning into subsets the set of elements combining into the k equal 2 groups. So each of these set of elements combined into k equal 2 groups produces its successive set. This mechanism produces set complexity, as you can see. There's quite a bit of complexity when these get broken down and partitioned. This mechanism produces set complexity, or makes what we term a set into a system.